So it would look like that to look neater. So your job is to look at it though and remember there's a limit happening behind it, and we know how to evaluate the limit. So I'm gonna, for now at least, I'm gonna turn it back into a limit so we can see it and we can use our limit rules to evaluate it. You guys already know how to do the limit rules. So this, all this stood for limit as n approaches infinity of a sum from 1 to n being infinity. So again, realistically, I can't actually go to infinity. We're going to just imagine it for now, of the function, but when we wrote it down in this format, it said x sub I. So I'm going to put x sub I where it currently says x squared.
These are easy. These are stuff in spot.
Sweet. Dx in the limit format, they write delta x. Now, I don't want you to get too caught up in that, but I just want you to see them both and remember they are the same. So our job with a limit, remember, is to get a function, reduce the function, get an answer. You guys are pretty good at that. So we need to get this to look like functions. So I want you to pay attention just to the sum part of it. And I want you to think about the pieces. It's the sum of this function squared and this delta x. First of all, let's take that delta x. What does that look like? Like, where does it actually come from? The width of the rectangle. Think about the work you talked about with your neighbor.
It's the interval.
You told me, well, it has to do with the interval, but you told me when you did 4 rectangles, the width was 0.5.
Well, if 2 is the thing, we need. Well, if it's an infinite number of parts, how am I supposed to tell? Because it's just that.
It's n parts.
So 2 over n.
Where did the 2 come from?
That's your boundary of where you're solving to.
So if I'm going to call it from 0 to 2, you're saying it'd be 2. What if I called it from A to B, just for later sake? What's the math I do?
B minus A over 2.
Okay. I'm going to do this in a different color. Super fun. So B minus A over n being the number of rectangles. So in this case, you said 2 minus 0 over n, which is 2 over n. That is what the delta x actually is for this problem. Yep, we're going to actually write that in a second instead. But I want us to also change this x sub I into a function, because that looks kind of nasty too. So x sub I, let's talk about him a little bit. The x sub I is the actual x value that you're going to plug in and square. So when you guys did this a few minutes ago, you plugged in 0.5 and squared it the first time. Then you plugged in 1 and squared it. Then 1.5 and squared it. And then 2 and squared it. How did you figure out what number to square?
It would be something plus delta x.
Good, because I'm always just moving another.
A plus delta x.
You see where he's getting that? I'd start with 0. The first time I add 0.5. Now the second time though, the second number is 1.
Delta x.
So how would you express it? You're saying take the first number, the A, and add on
B
delta x the first time,
And you just.
but then the next time I'd have to take 2 delta x's.
Well, can you just write that as a series somehow?
And then the next time I'd have to
Would
take
you write it with the
3
sigma?
delta x's.
Would you write that with the sigma? then?
Where's where is that number coming from? I'm not going to add another sigma. Instead, I just want to express, like, how do I find that number? It's always
It
A
would
plus
be
something.
A
It would
times.
be m delta x.
But would it not be an
1, 2, and 3. You're almost there. A plus what delta x?
So wouldn't it be
N represents how many rectangles. The question is, what rectangle number am I on?
I.
I'm on I. So good, you just had your letter wrong. Very good. So if I plug that in, and I plug in what I know, what was A in this problem?
0.
We need to plug in delta x if you want.
I can. That's I, 2 over n. Or in other words, 2I over n. If I were you, and I was highlighting things for future use, these 2 steps are important. This is always going to be true, no matter the problem, and this is always going to be true. So those 2 things are like the equations. The rest of it to the right is just for this problem. So those would be things that I'd want to like highlight to myself to say I'm going to have to find these 2 things every time so that I can go back and turn this limit into a function. So this limit up here, the reason I just found those 2 pieces was to actually replace delta x and x sub I. I want to replace them with things that actually look like functions, so it doesn't look so messy, so I can evaluate the limit. So I'm going to rewrite my problem with those plugged in. I equals 1 to n. X sub I is 2I over n. Set square it and multiply it by delta x.
Well, could you, oh wait, that's specific to our problem. I was gonna say, could you square that every single time?
Yeah, and so that is only true for this problem, but we can do it in this case. So I do think we should do that next.
I mean, no, it just makes it longer. I was gonna say, like, no, it totally defeats the purpose. It just did. I should be like, you can just put x sub I in there.
Oh, I see where you're going with that. So now that it's at least all in i's and n's, we can combine them. You couldn't combine the x sub I and the delta x up there, but I do see stuff that I could clean up here, so.
Before I squared.
Good,
N squared.
good. Now, can you even take that one step further? What's 4i squared times 2?
8i squared.
Okay, so I have 8i squared. And you said n squared, Bree? Multiply by another n. N times n is what? N times n. Okay, but what if I had n squared and then I did another n? There we go.
Is that the answer?
Well, I have to take the limit of that as n approaches infinity of that sum. Okay.
Well, I always equal 1.
I will always start at 1.
Sorry.
And then it's going to go to 2. And then it's going to go to 3. And then 4. And then until I hit n, which is actually what we want to be infinity. Let's look at that. I'm going to write down what Max and Bree just put together. They said this sum is actually, so I'm not going to write the sum symbol because I'm going to write what they just did mathematically. They said I would be 1, and then it would be 2,
Yeah.
Oh, gosh, thank you. Just change the whole problem. And then it would be 3. And it would keep doing this until it turned into infinity. Or, well, in this case,
Well, I
we
mean,
can write n.
Just keep going.
Yeah.
And now is where we do the sum of infinite series? On the top, at least?
Do you see a series?
Well, yeah, since we can't do the series on the bottom, since it's always the same, we can do the sum of an infinite series on the numerator, correct?
What do you see changing in terms of the pattern?
It's just adding 1 every single time.
Okay. Every time though, you're saying the bottom stays the same and part of the top stays the same, right?
So it's just over 1 if you want to do it as a fraction.
For the part that's actually doing a pattern?
Yeah, wouldn't it be like, for this problem, it'd be like 8 times I or x sub I plus 1.
Like this up here? Oh, you're looking at actually what is the series? Yeah, we'll get to that series, but what he's saying is that what he sees is the 8 and the n cubed, those repeat. So that's the good news. But this is being multiplied by 1 squared, and then 2 squared, and 3 squared,
Oh, so
all the way until I hit n squared. This is the series that he's recognizing. And there is a way of writing that that's nicer.
Oh, we've done this before, correct?
Back when we did infinite series, we did find a different way
Is
of
it
doing it.
something factorial?
Do you remember doing those?
Something minus the ratio minus
They're in our book.
a sub 1 over r.
If only you knew the pattern, huh?
Yeah, if only I had my old notebook that had that in it.
Because we had a pattern for that we could turn into n's, and then all we'd have to do is do the limit. And life would be grand.
Geometric series of sequences, infinite series and sequences.
I will tell those of you who aren't digging back to that section, they did remind us of some of them on page 962 of your book. I might not even write it down today, but I just want you to find them. You look on page 962 in the bottom corner. They wrote some different series for you. It looks like this. Find this. And they wrote down some of them.
Yeah, I'm on the right page. 775 is the
Did they also?
lesson.
They told you the patterns too. Does it match this guy? Which one do we have?
No, there's stuff. We have the.
We have the second one. So we got this guy. That's what we can replace him with.
So you're gonna have to find limits.
So we'll replace him with that.
Oh, and that's the
And
function that
then
you
we
use.
can do the limits. Yeah, that's a function that simplifies to that.
Okay.
So where we wrote all that, we were in that.
Correct.
Oh, and then you find the
And
limit
then we're
of
ready to
that,
take the
and then
limit.
You're done.
And we're done. Absolutely.
You know.
So I'm just gonna write it for today, and then we'll actually take the limit tomorrow, because that's the easy part. So, let's see here. I'm gonna replace him with that guy. And we do still have that 8 over n cubed. Don't forget him. Can you read it to me, Bree?
Into n times n minus 1 times 2n plus 1 over 6.
Sweet. So we're just gonna have to simplify and take his limit tomorrow. But he'll be easy then.